Welcome! Let's take a look at minimizing the construction costs for a container. A rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of its base is twice the width, and the material for the base costs $12 per square meter. The material for the sides costs $8 per square meter. Find the cost of materials for the cheapest such container. So notice that in this particular instance, we are trying to minimize the cost of the construction of the container. So first of all, let's consider what this container looks like. A rectangular container would resemble something like this, where the ends are possibly squares, possibly rectangles. And the base is a rectangle. And what do we know about the base? We know that the length of the base is twice the width. So if we let this side of the base be the width, then the length is the other side of the base, and that is 2 times the width, or 2W. Now, we don't know anything about the height, so we'll just call that H for the height of the container. We're interested in minimizing the cost, so let's think about the cost for constructing this container. We know that the base will cost $12 per square meter, and we know that the sides cost $8 per square meter. I lost my 8. Okay, what else do we know? There's one other piece of information here. That is about the volume of the container. So we also know that the volume of the container needs to be 10 cubic meters. Well, based on the labeling and construction of our container here, that would be W times 2W times H, or 2W squared H is our volume. And now, so that's our constraint. And now to determine our objective function. So our objective function, our objective here is to minimize cost. So let's look at the cost. We'll call that function C. And so we noticed that the cost depends on whether we're building the base or the sides. The base costs $12 per square meter. So if we focus on the base, we're going to have $12 times the area of the base. The area of the base is W times 2W. Now, each of the sides, the cost will be $8 per square meter. So we will have 2 sides that are dimensionally W and H, W by H, this front side and this back side. There are 2 of those. So we'll have 2 sides that cost $8 per square meter, and the area of those sides are W times H. And then we'll have 2 sides that are 2W by H, this side on the left and this side on the right. So we'll have 2 sides like that. So we'll have 2 sides that are $8 times 2W times H. So let's simplify this up just a little bit. Our cost function is going to be, our first term will be 12 times 2, or 24, W squared. And notice that our second 2 terms have variables w times h. So we can combine those. So we've got 16 in the first term. So this is 16wh. And we have 16 times 2, or 32wh from the third term. So 16 plus 32 is 48wh. So our objective function is going to be c is equal to 24w squared plus 48wh. Now the function that we want to minimize is cost, but currently cost is a function of two variables, w and h. So let's go ahead and use our constraint to solve for h and then substitute that information in for h in our objective function. So if we solve the constraint equation for h is equal to, and we'll divide both sides of the equation by 2w squared. We get 10 over 2w squared, or we can simplify a bit and get 5 over w squared. That's not a squared. Okay, so now let's replace that within our objective function. So our function c is now 24w squared plus 48 times w times 5 over w squared. So we can simplify this a little bit. The w's will divide out, leaving us with 1w in the denominator. So we have 24w squared plus, let's see, 48 times 5 plus 240 over w. Now, in order to find the derivative more easily, we'll rewrite c as 24w squared plus 240 times w to the negative 1 power. So let's go ahead and find our critical points. So c prime equals 2 times 24 is 48w plus 240 times negative 1w to the negative 2 power, or 48w minus 240 over w squared. Now, in our search for critical points, we'll need to be able to set this equal to 0. Let's go ahead and multiply 48w by w squared over w squared. So at this point, our derivative is 48w cubed minus 240 all over w squared. Now we have two sources for critical points. The first source of critical points is where c prime is equal to 0. The second source of critical points is where c prime does not exist. And so as we look at our derivative function here, we can see that c prime does not exist when w equals 0. Now, as we consider the context of this problem, if w equals 0, we don't have a container, and so this is not of any particular interest in the context of this particular problem. In fact, we would expect that the height and width of this sides of this box or container could be any positive number. So let's come back and look at the first source of critical numbers, that is where this derivative equals 0. And so if this derivative were to equal 0, the numerator would have to equal 0. So let's look at where 48w cubed minus 240 equals 0. Solving this, we'll get 48w cubed equals 240 if we add 240 to both sides. Then if we divide both sides of the equation by 48, we'll end up with w cubed is equal to 5. And then taking the cube root of both sides of this equation, we find that w needs to be the cube root of 5. And just so we know the approximate size of this width, this is approximately 1.710. Now let's go ahead and confirm that we have in fact minimized the cost of this container. So recall that our derivative was 48w plus 240 times negative 1w to the negative 2. That function is not too difficult to find the second derivative, so we'll go ahead and use the second derivative test on this value for w. So our second derivative, the derivative of 48w is simply 48, and then if we take the derivative of the second term, we'll have plus 240 times, and then this negative 1 will be multiplied by negative 2, so we'll have a 2 times w, and subtracting 1 from the exponent, we get a negative 3. So we have 48 plus 480 over w cubed. Now, with the second derivative test, recall that all we're interested in is whether the second derivative is positive or negative at the critical point. So c double prime at our critical point, cube root of 5, is going to be 48 plus 480 over the cube root of 5 cubed. So we have a positive number plus a positive number. So that is definitely going to be a positive number. And so because the second derivative is positive, we know that the function is concave up, and we have a relative minimum at our critical point. And so now we know we have a minimum where w equals the cube root of 5, which is approximately 1.701. Now, remember, we're trying to minimize the cost of construction, and here is our cost function. We could go ahead and just evaluate our cost function with this value of w. So we could say that cost is equal to 24 times the cube root of 5 squared plus 240 over the cube root of 5. Now, at this point, we could rationalize or combine and get a common denominator. So we could multiply the first term by the cube root of 5 over the cube root of 5, which would then give us our cost being 24 times the cube root of 5 cubed plus 240, all divided by the cube root of 5. Well, on the cube root of 5 cubed, that's 5. So we would have 24 times 5 plus 240. So in our numerator, we would have 120 plus 240, so 360 over the cube root of 5. Now, this cost needs to be expressed in dollars. So let's go ahead and approximate this to the nearest cent. And so to the nearest cent, this would be $210.53. So now we can state our conclusion. So we say that the minimum cost for manufacturing the box is $210.53. I hope you find this helpful.